What if the very fabric of our digital world, the silent engine churning behind every tap, swipe, and spoken command, suddenly changed its tune? What if the gritty, clunky flow of electrons pushing and pulling through microscopic wires gave way to an ethereal dance of light? This isn't a scene from a science fiction movie. It's the burning question, the what if, that ignited a quiet revolution at the University of Pennsylvania. Their new photonic chip isn't just an incremental upgrade. It's a world first, a technological marvel that harnesses light to both process and train artificial intelligence models. But why should you, someone who might prefer to spend their time binging the latest streaming series rather than dissecting microchips, care about this intricate piece of silicon and light? Because this chip could fundamentally rewrite your daily experience, altering everything from how quickly your phone leaps to attention to how much energy your favorite apps quietly consume behind the scenes. It's about to make the digital world faster, cooler, and profoundly more intelligent. Are you ready to see your future in a new light? To truly grasp the seismic shift this represents, let's pull back the curtain on the technology that underpins our lives right now. Every morning, when you ask your virtual assistant about the weather, every time you rely on GPS to skillfully navigate rush hour, or even when you just scroll through an endless feed of content, you're unwittingly engaging in a furious ballet of billions of electrical signals. These signals zip, crisscross, and collide within the intricate labyrinth of silicon chips, tiny, powerful brains that are, frankly, modern marvels. They've powered our world for decades, shrinking in size while exponentially growing in capability, pushing the boundaries of what we thought possible. Yet, even these champions of computation are now pressing against fundamental limits. They generate significant heat, demanding elaborate cooling systems that hum and whir in our laptops and scream from data centers. They guzzle energy, turning vast amounts of electricity into the heat we feel emanating from our devices, a stark reminder of their tireless yet often inefficient work. And, perhaps most critically, they're beginning to struggle to keep pace with the insatiable demands of modern AI, a field that requires truly staggering computational power just to learn and then adapt, mimicking the complexities of human cognition. Now pause and truly imagine swapping out that clunky heat-generating electricity for the pure, unadulterate elegance of light. Photons, those fundamental particles of light, are nature's ultimate messengers. Unlike electrons, which carry a charge and interact with materials in ways that create resistance and heat, photons are essentially massless and charge-neutral. This means they move at the absolute speed limit of the universe, the speed of light. Imagine data streams that don't just travel fast, but instantaneously from a human perspective within the chip. Even more remarkably, photons possess an incredible ability to carry multiple data streams simultaneously, a property known as multiplexing. Think of it like this. An electronic wire can typically send one signal at a time, like a single-lane road. A photonic waveguide, however, can be engineered to carry many different signals at once, each encoded on a different color wavelength of light. Like a superhighway with hundreds of lanes, all flowing in parallel. And here's the kicker: they barely sip energy, moving through optical fibers or waveguides with minimal loss, virtually frictionless. This isn't just an incremental improvement. This is the audacious promise of photonic computing, a future where machines process information, analyze complex patterns, and literally think with the dazzling speed and efficiency of light itself. What would it feel like to never wait for an app again? to have your devices anticipate your needs with instantaneous precision. This is the future photonic computing is beginning to illuminate. But, as with all groundbreaking innovations, there's a formidable catch, a seemingly insurmountable hurdle that has kept this dream largely confined to scientific papers and whispered possibilities. Controlling light is akin to trying to herd 1,000 wild cats while simultaneously riding a unicycle blindfolded through a labyrinth. Electrons, for all their tiny complexity, are relatively obedient. They carry a charge, which means they can be easily manipulated by electric fields, guided through circuits like water through meticulously laid pipes. We've spent over a century perfecting the art of electron wrangling, building an entire civilization on its predictable flow. Photons, on the other hand, are wild and free. They don't carry a charge, making them notoriously difficult to steer, trap, or force into the precise non-linear interactions required for complex computation. Imagine trying to make two beams of light interact meaningfully without simply passing through each other. It requires engineering at an almost unimaginable level of precision, bending light to our will without losing its incredible speed or efficiency. The Penn team's breakthrough is not just a testament to scientific brilliance, it's a heroic saga of human ingenuity, a monumental step towards taming these wild photons, forcing them into formation, and commanding them to do our bidding in ways previously thought impossible. Imagine a world where your phone remains cool to the touch even after hours of intense gaming, where your laptop battery lasts not just for a day, but for days on end, and where every device processes information in a fraction of the time you've come to expect. How would that truly change your day-to-day life? Would you finally be able to binge-watch an entire season of your favorite show on a single charge without your laptop overheating into an uncomfortable lap warmer? Would the prospect of self-driving cars reacting to unexpected obstacles with the speed of thought instantaneously and flawlessly finally bring you a sense of absolute trust and peace of mind on the road? These aren't just idle questions. They are the tangible impacts of bringing light into the heart of our machines. To fully appreciate the magnitude of this technological leap, consider the grand sweep of human innovation, a story told in powerful analogies. Think of the monumental shift from the ponderous yet revolutionary steam engine to the sleek, explosive power of a rocket ship. The steam engine, with its belching smoke and clanking pistons, powered the first industrial revolution, fundamentally transforming manufacturing, transportation, and daily life. It was a marvel for its time, but bulky, inherently slow, and incredibly inefficient compared to the technologies that followed. Similarly, today's electronic chips, while undeniably impressive and the bedrock of our digital age, are akin to the peak of the steam engine era. They are reaching their physical limits, bound by the very physics of electron flow. Now, imagine the leap to a rocket ship. A rocket doesn't just do what a steam engine does, but faster. It opens up entirely new frontiers, reaching places previously unimaginable. This is precisely the kind of paradigm shift photonic chips represent. They don't just process data faster, though that's a significant part of it. They do it with a mere fraction of the energy, potentially achieving efficiencies that are 10 to a staggering 1,000 greater than their electronic counterparts. For artificial intelligence, a field that is notorious for its voracious energy appetite, particularly during its intensive training processes, this isn't merely a game changer, it's a civilization-level transformation. Let's contextualize this with a real-world example, one that has undoubtedly touched your life, even if you haven't consciously considered its hidden cost. Training an advanced AI model, like the colossal neural networks that underpin ChatGPT or other cutting-edge language models, is not just a computationally intense endeavor, it's an energy behemoth. It can consume as much electricity as a small town in a single training run, burning through megawatts of power and generating a carbon footprint equivalent to a significant flight or industrial operation. Data centers, those unassuming warehouses filled with humming servers, are not just repositories of digital information. They are, quite literally, digital furnaces, burning through astronomical amounts of electricity to keep our online world running, driving up energy costs for everyone and placing immense strain on our global power grids and environmental resources. Now, truly picture a photonic chip, a device that can slash that energy bill not by a mere 10% or 20%, but by orders of magnitude. Imagine the collective sigh of relief as AI suddenly becomes dramatically cheaper to develop, tearing down the financial barriers that currently limit innovation to only the largest tech behemoths. This shift would make AI development far more accessible to smaller companies, to university researchers, and even to individual innovators with brilliant ideas but limited budgets, fostering a vibrant, decentralized ecosystem of discovery. And most profoundly, it means AI becomes less taxing on our planet, transforming a nascent, energy-hungry technology into a sustainable one, ensuring that the incredible innovations of the future don't come at the unbearable cost of our environment. This isn't just about making tech better, it's about making our future possible. But the transformative benefits of photonic chips extend far beyond simply cutting energy bills. They offer a fundamentally different way of handling data, one that unlocks unprecedented levels of parallel processing. This is achieved through the magic of multiplexing, a process that allows a single optical channel to carry multiple independent data streams simultaneously. Let's revisit our juggling analogy, but make it more vivid. Imagine you're a master juggler, expertly keeping 3 balls in the air while effortlessly riding a unicycle. A conventional electronic chip, with its sequential processing, is like trying to juggle only 1 ball at a time, catching it, processing it, and then sending it off before picking up the next. It's effective, but inherently limited by its serial nature. A photonic chip, however, can truly keep all 3 balls or hundreds or thousands in the air simultaneously. Each ball represents a different stream of data, perhaps encoded on a different color of light, or oscillating at a different frequency, or even polarized in a different direction. All these distinct information packets travel through the same tiny waveguide at the same time, without interfering with each other. This means a radical acceleration of processing for complex, multifaceted tasks, the very tasks that AI excels at. Think about the speed required for instantaneously recognizing faces in a crowded photo gallery, or for predicting highly volatile stock market trends in real time, where milliseconds can mean millions. For you, the end user, this translates to apps that load not just quickly, but instantly, responding to your touch or voice before you even consciously register the command. It means games with a level of lifelike graphics and environmental complexity that blurs the line between virtual and reality, processing visual information with unparalleled speed. It means medical AI systems that can scan and diagnose diseases from complex imaging like MRI or CT scans in mere seconds, potentially saving lives by enabling earlier, more accurate interventions. What would it genuinely mean to have technology that seems to anticipate your needs, understanding your intent, and providing solutions before you even articulate them? How would that reshape your relationship with the devices that define your digital existence? Here's where the narrative of photonic computing gets truly fascinating, dipping into the very essence of what makes AI intelligent. Artificial intelligence isn't merely about crunching numbers at lightning speed, though it certainly does a lot of that. It's about learning, adapting, recognizing subtle patterns, and making sense of the world in ways that uncannily mimic human thought. At the very core of this profound ability lies something called non-linearity, a concept that, while sounding dauntingly complex, is surprisingly relatable. Think about how you would teach a child to recognize a dog. You wouldn't just show them one picture and declare, "This is a dog." You'd show them a golden retriever, then a chihuahua, then a poodle, then a scruffy mutt. You'd point out common patterns: floppy ears, wagging tails, furry coats, a certain way they move or bark. Slowly, through this iterative process of varied inputs and subtle transformations, the child learns to spot a dog in any context, no matter the breed, lighting, or pose. That, in essence, is non-linearity in action. Small, seemingly disparate inputs, like the individual pixels in a photo or the nuances in a spoken word, are transformed in complex, non-proportional ways to lead to big, meaningful, and often highly complex outputs, like accurately identifying a dog, understanding a command, or generating a coherent paragraph of text. It's the magic ingredient that allows AI to generalize, classify, and truly learn. Electronic chips, thanks to decades of transistor development and sophisticated mathematical functions, handle this concept of nonlinearity with relative ease. Their transistors can be switched on or off, acting as tiny gates that apply these mathematical transformations, effectively bending the input data into new, more meaningful forms. Photonic chips, however, have historically stumbled at this crucial hurdle. Light, in its natural state, is incredibly linear. It's fantastic for simple, direct tasks like adding numbers together or multiplying them, racing through waveguides without fuss. But when it comes to the intricate, nuanced transformations required for deep learning, for tasks like pattern recognition, decision-making, or natural language processing, light has been like a world-class sprinter who simply can't turn corners. It lacks the inherent flexibility to interact with itself or with materials in ways that produce those complex, non-linear patterns. This fundamental limitation has been the Achilles heel of photonic AI, largely confining it to theoretical models or niche applications, unable to truly compete with its electronic cousins in the realm of advanced machine learning. Until now. The Penn team's groundbreaking chip fundamentally changes this game, not by fighting light's linear nature, but by subtly coercing it into non-linear behavior. They achieved this by integrating a very special type of semiconductor material into their photonic chip, a material that possesses a unique sensitivity. It responds to a secondary beam of light, what they ingeniously call a pump beam. Imagine this pump beam acting like a master conductor in an orchestra. The main signal beam carrying your data is the orchestra itself, playing its linear melody. But the pump beam, by subtly modulating its intensity or wavelength, can dynamically alter the properties of the semiconductor material through which the main signal beam passes. This dynamic alteration, in turn, subtly bends or twists the main signal beam in a non-linear fashion. Picture an artist meticulously painting on a digital canvas, where each stroke of their brush doesn't just add color, but dynamically changes how light itself passes through the canvas, altering its very texture and refractive index. The pump beam performs a similar feat, constantly, dynamically, and programmably altering the chip's optical properties, allowing it to perform those crucial non-linear transformations that are the bedrock of sophisticated AI learning. This isn't just a clever trick, it's like giving light the equivalent of a thinking brain, enabling it to bend and twist into the intricate patterns that mimic the complexity of human learning and decision-making. How would it genuinely feel to know that the AI embedded in your devices isn't just blazing fast, but is capable of thinking and processing information in a way that is profoundly closer to how your own human mind works, perceiving nuances and patterns rather than just brute-forcing calculations?
What truly elevates this pen chip from a remarkable scientific achievement to a potentially revolutionary technological breakthrough is its inherent programmability. Consider the vast majority of existing photonic systems. Once fabricated, they are essentially like a finished painting on a canvas, beautiful, intricate, but ultimately set in stone. If you design a photonic chip for a specific function, say to perform a Fourier transform, and then later decide you need it for a different task, like a complex neural network multiplication, you'd typically need an entirely new chip, requiring a fresh, expensive, and time-consuming manufacturing process. It's a rigid, single-purpose approach that severely limits versatility and widespread adoption. But the pen chip shatters this limitation. It's not a finished painting, it's a dynamic digital canvas, endlessly adaptable and reconfigurable. By simply tweaking the properties of that pump beam we discussed, its intensity, its wavelength, its pattern, engineers can instantly and seamlessly reconfigure how the chip processes data. It's like having a single piece of hardware that can transform its very computational architecture on the fly, tailoring itself to the specific demands of the task at hand. Imagine for a moment that you are a gourmet chef. But instead of needing a separate oven for baking cakes, a specific grill for steaks, and a different fryer for potatoes, you have a single magic stove that can switch from exquisitely baking a delicate soufflé to perfectly grilling a thick-cut steak or even deep-frying crispy calamari, all with a simple command and no physical modification. That's the unparalleled flexibility this chip offers. A singular piece of hardware that possesses the chameleon-like ability to not only run pre-trained AI models, but also train them from scratch, and then continually adapt to new data, all powered by the speed and efficiency of light. This unprecedented versatility could single-handedly democratize AI development, liberating innovation from the clutches of tech giants with their multi-million-dollar data centers. Suddenly, smaller teams, university labs, and nimble startups could experiment, iterate, and develop cutting-edge AI without needing to build a colossal infrastructure. For you, the everyday user, this could manifest as hyper-personalized apps that learn your unique habits and preferences in real time, not over days or weeks, but instantly. Think of a fitness tracker that doesn't just log your activity, but dynamically adjusts your workout plan, giving you real-time feedback and adapting as you improve your strength or endurance, always pushing you just the right amount. Or imagine a virtual assistant that doesn't just answer questions, but genuinely gets smarter with every conversation, anticipating your needs and offering solutions before you even fully articulate them, becoming a truly intuitive extension of your thoughts. The Pen team, not content with merely theorizing, put their revolutionary chip through its paces, testing it on classic AI tasks that serve as benchmarks for machine learning performance, and the results were nothing short of stunning. In one crucial test, designed to evaluate the chip's ability to classify and separate data points, it flawlessly drew complex decision boundaries with over 97% accuracy, a performance that not only rivaled but in some cases even surpassed leading electronic AI systems. In another widely recognized benchmark, it tackled the venerable iris dataset, a foundational challenge in machine learning used to test classification algorithms, achieving over 96% accuracy. This isn't just about raw numbers, it's about proving that light, when tamed by human ingenuity, can perform sophisticated AI computations with incredible precision. But what made these results even more profoundly impressive was how it achieved this. The photonic chip accomplished these feats with significantly fewer components than its electronic counterparts, translating to simpler designs, lower manufacturing costs, and greater reliability. And, of course, it did all this while consuming drastically less energy and operating at the theoretical speed of light. Imagine a future where your smart home isn't just reactive, but truly anticipatory, knowing when you're about to arrive, precisely adjusting your thermostat to your preferred comfort level, preheating your oven for dinner, and even proactively ordering groceries based on your consumption patterns, all powered by the quiet, efficient, and instantaneous intelligence of light.
There's a beautiful, almost poetic symmetry to this groundbreaking achievement, a historical resonance that adds an extra layer of significance. The University of Pennsylvania, the very institution where this photonic revolution is unfolding, holds a hallowed place in the annals of computing history. It was here, in the 1940s, that the ENIAC, the Electronic Numerical Integrator and Computer, the world's first electronic digital computer, was born. That colossal machine, a room-sized behemoth of vacuum tubes, wires, and switches, consumed enough electricity to power an entire small neighborhood, generated immense heat, and required constant maintenance. Yet, it was a monumental leap, ushering in the electronic age of computing. Now, 8 decades later, the same hollowed halls are pioneering a chip that seeks to gracefully replace that clunky, power-hungry electricity with the sleek, efficient flow of light. It's as if computing is completing a grand historical circle, evolving from its loud, power-hungry infancy into something elegantly quiet, astonishingly efficient, and almost magical. It's the ultimate upgrade, a transformation from the mechanical to the ethereal. This isn't just about indulging in nostalgia, it's about unlocking unimaginable potential. The Pen chip is more than a prototype. It's a tantalizing glimpse into a future that radically reshapes our digital infrastructure. Imagine data centers, those sprawling, energy-devouring complexes, shrinking dramatically in physical footprint and power requirements. Imagine energy costs for computational power plummeting to fractions of what they are today. And most importantly, imagine AI, that powerful tool for progress, becoming accessible to everyone, not just the exclusive domain of a handful of tech giants with vast resources. This technology has the potential to level the playing field, making innovation more inclusive, more widespread, and far more impactful. Consider a small rural hospital that could suddenly leverage photonic AI to analyze complex medical scans for early disease detection in mere seconds, offering world-class diagnostics regardless of its budget. Or picture a burgeoning small business, previously locked out by the prohibitive costs of AI, now able to harness its power to predict market trends, optimize logistics, or personalize customer experiences without breaking the bank. What deeply personal or community-level problems in your own life or in the lives of those around you could a faster, greener, and more accessible AI genuinely solve? What frustrations could it alleviate? What opportunities could it unlock? Of course, no true revolution, no matter how dazzling its promise, unfolds without its inherent hurdles and formidable challenges. Photonic chips, for all their groundbreaking potential, are still in their infancy, akin to the early days of the internet or the nascent automotive industry. scaling them up to handle the truly staggering complexity of modern AI models, the ones powering advanced language models that write poetry, or the intricate perception systems in autonomous vehicles that navigate chaotic city streets, will take considerable time, concerted effort, and brilliant engineering. Manufacturing these chips is no small feat. It demands precision at the nanoscale, akin to carving an impossibly intricate sculpture with a laser beam, ensuring every waveguide and modulator is perfectly aligned. And then there's the software challenge. Our entire software ecosystem, from operating systems to programming languages to AI frameworks, has been meticulously built and optimized for electronic processors. A complete reimagining of software will be necessary to truly harness the full raw power of photonic processing, a process that will take years of collaborative effort across academia and industry. But despite these significant obstacles, the roadmap is clear, and the potential, in the truest sense of the word, is limitless.
Think back to the early, sputtering days of the internet. It was a slow, clunky, often frustrating experience, limited to a few intrepid tech enthusiasts and academic institutions. Yet, within just a couple of decades, it utterly transformed how we connect, how we work, how we learn, and how we live, becoming the ubiquitous backbone of our modern world. Photonic computing could very well follow a similar trajectory, beginning as a curious lab phenomenon and steadily evolving to become the foundational backbone of our entire digital infrastructure. Picture a future where AI-powered devices aren't just common, but as ubiquitous and unnoticed as light bulbs, each one running on a chip that literally thinks with light, operating silently, efficiently, and with incredible speed. How would that fundamental shift change the way you interact with technology? Would interfaces become invisible, actions intuitive, and information seamless? Would your personal digital assistants become true companions, understanding your every nuance? The captivating story of the photonic chip isn't just a tale of technological prowess or scientific ingenuity. It's a powerful narrative about the indomitable spirit of human curiosity and our relentless drive to push beyond perceived boundaries. It serves as a profound reminder that true progress, the kind that reshapes civilizations, very often begins with a simple yet audacious question: what if? What if we could escape the physical limits of electronics and make machines truly think with light? What if we could redefine AI to be not just powerful, but inherently sustainable, a force for good that doesn't deplete our planet's resources? These questions, born in the quiet contemplation of a university lab, could ripple out to touch every corner of our lives, from how we learn and communicate to how we care for our planet and each other. For you, the curious individual navigating this ever-evolving world, the profound lesson is beautifully simple, yet incredibly powerful. Embrace the unknown. The next time you find yourself staring down a challenge, whether it's a daunting work project, a deeply personal goal, or a grand dream for the future, don't just accept the status quo. Instead, take a moment, pause, and ask yourself that transformative question: what if? What if the established path isn't the only path? What if the impossible is merely the untried? That single question, fueled by genuine curiosity, can spark innovation not just in labs, but in your own life. The Penn team didn't settle for the limitations of current computing. They reimagined computing itself, blazing a new trail. You too possess the incredible power to reimagine your own world, one curious question, one bold idea at a time. As we stand here on the very cusp of this photonic revolution, I invite you to linger on that thought and ponder: what's the next what if that's stirring in your own life?
How can you harness that innate human curiosity, that spark of wonder, to create something truly new, to solve a problem that seems insurmountable, or to achieve a dream that feels just out of reach? Share your reflections, your what-ifs, and your ideas in the comments below. I would genuinely love to hear your thoughts and see the light you can cast on the future. And if this story, this glimpse into a future bathed in the elegance of light, has sparked your imagination and fueled your sense of wonder, please consider subscribing to our channel for more tales of human ingenuity, innovation, and discovery that are shaping the world around us. Here's to a brighter, healthier future for you, for all of us, and for the incredible world we share. Stay curious, stay healthy, and together, let's light up the future.